Okay. Are you able to see my screen?
Yes, sir.
Yes, sir.
Okay. So let me recapitulate. Oh, come on. We've been solving a particle in a bog or a particle in an infinite potential well. Okay, so you have a potential well where the V equals infinity on either side, and in this region V equals 0. Okay, so this is x equals 0 on this point, and here is x equals a, and we were trying to solve the Schrodinger's equation for this setup. Okay, the particle is somewhere here, somewhere in the middle. Okay, now our goal is to find the wave function. What is the wave function? Okay, and you guys remember that wave function is basically probability amplitude for finding the particle at any point x at any time t. Okay, so psi of x comma t is probability amplitude for finding the particle at x t, right? And psi of x comma t square is probability of the same thing, probability for finding the particle at x comma t. Okay, you guys know this. For by now, you guys must have gathered this much. All right, so our goal was to solve Schrodinger's equation for this particular setup. And remember, we used separation of variables, meaning that x and t can be this. So basically this function, let me write this as this capital psi. Okay, capital psi. So this capital psi can be written as some small psi of x and phi of t. Okay, basically this is called a separation of variables approach. Okay, most functions cannot be separated this way, but we will nevertheless proceed. Okay, we will see that later on we can create functions from this approach. We can create functions that are non-separable. You cannot separate x and t in the final solution. You cannot do this. X and t cannot be separated. But in the meantime, during the derivation, you can separate it and do the calculations. Okay, it's a common approach. Okay, so we did this, and we substituted this in the Schrodinger's equation. H cross dou by dou t of psi equals h psi, where h is h bar square over 2m dou x square plus v. Sorry, there is a minus here. Minus h bar square over 2m dou square by dou x square plus v. Hello? Are you guys with me?
Yes, sir.
Yes, sir.
Yes,
Yes,
sir.
sir. Yes, sir.
Okay, is Neil Sherwin Kujur? Is he part of the class? Neil?
Yes, sir. Yes, sir.
Yes,
He's
sir.
in
Yes,
our
sir.
class.
Yes.
All right. So what we did was to supply. Okay, basically this is capital psi. I'm sorry, I keep messing up. So capital psi is psi x phi t, and then we do the separation of variables. We did this last time. Do you want me to do it again, or can we just proceed? Deep silence.
Could you just go through it once, basically?
Okay.
Second week,
So-
let's go.
Okay, so so what I'm going to do is to substitute this for the capital psi there. Okay, so it's ih cross dou phi by dou t, because phi is just a function of t, and psi is a function of x, and h is all function of x. Okay, there is no t on that side, so you can take the t part out, that is phi part out, and then minus h bar square over 2m dou square by dou x square plus v psi, small psi. Okay, now you can divide by phi of t psi of x on both sides. Okay, phi of t psi of x on both sides. So this psi of x cancels off and this phi cancels off. Okay, so what you get is basically 1 over phi of t ih cross dou phi by dou t equals minus h bar square over 2m dou square psi by dou x square plus v psi divided by psi 1 over psi. Okay, so far so good. Okay, now this side is completely a function of t and this side is a function of x. Okay, if they are to be equal, they must be constant. This must be equal to a constant, and we argued about this last time. It cannot be a function of x or t. If it is a function of x, then if you change x, the right hand side is going to change. If it is a function of t, if the constant is a function of t, then if you change t, the left hand side is going to change, whereas the right hand side is going to be a constant. So they cannot be equated at all times and space. At all x and all t, they must be the same, which means you can equate it to a constant E. Okay, E is energy. Right. Okay. E, as I said, is energy basically. Okay. It's a constant. Okay. So you can equate both the sides to a constant E. So 1 over phi ih cross dou phi by dou t equals E, and on this side it's h psi equals E as well. Sorry, 1 over psi. H psi 1 over psi equals E as well. Right? Right? If you solve this, you will see, if you solve this, you will see phi of t is some e power minus I e t over h cross. And if you solve this, it's knocking. And if you solve this part, you have to be careful about solving this part because h is a function of x. Okay. So what we're going to do is to solve E psi. Okay. So this is called time independent Schrodinger equation. H psi and E psi, H psi equals E psi is a time independent Schrodinger equation. The time we have factored out the time. So the time factor is here. Okay, so whatever solution we get here has to be multiplied by that factor to get the full wave function. The full psi is psi of x times e power minus I e t over h cross. Okay, this you need to get from this equation. So our goal is to find what is psi of x. Our goal is to find psi of x, small psi of x, lowercase psi of x. Okay, so how do we proceed? Look at the function, look at the potential. Okay, the potential is infinite here, v equals infinity here, v equals infinity here in these regions. So can the particle be on these regions, in these regions, below x equals 0 and above x equals a? Beyond x equals a, x equal to a, the particle cannot be found because the potential is infinity. Okay, if the particle has to be there beyond x equal to a, it must have an energy of infinity. That is when that is when it can go over to the be above the potential barrier. The barrier is infinitely long, infinitely high. Okay, so if it only if it has infinite energy, it is going to jump over that barrier. But no particle has infinite energy, right? So the particle cannot be found anywhere in this region. So basically your psi x less than 0 equals psi x greater than a is 0. You cannot find that particle anywhere. The probability amplitude for finding the particle below x equals 0 and above x equals a is 0. Does that make sense?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
So basically your particle is somewhere in the middle, and somewhere in the middle v is 0. Okay, you're assuming that the potential is 0. So basically your h boils down to minus h bar square over 2m dou square psi by dou x square. That's it, because the v is 0. Right? So h psi is basically minus h bar square over 2m dou square psi by dou x square equals e psi. That's it. What is the solution for this equation? Let's reframe it. Okay, dou square psi by dou x square equals minus 2me over h bar square psi, right? Okay, and you can call this, what is this, by the way? If you write E is p squared over 2m, p squared is 2me, right? And p is square root of 2me, right? Am I right?
Yes,
so, but
Yes,
p
sir.
is also h cross k. You know that, right? It's from h over lambda.
Yes, sir.
The de-Broglie wave.
Yes, sir.
So p is h cross k, which
Yes,
means
sir,
k
yes.
is 2me over h bar. K is 2me over h bar, right? So this is the wave. This is the wave vector. K is 2 pi over lambda. Lambda is the wavelength of the particle wave. Lambda is the wavelength of the particle waves. 2 pi over lambda is k. K is square root of 2me over h bar, right? So this is basically k square, right? So dou square psi by dou x square is minus k square psi, right?
Yes, sir.
So
Yes, sir.
psi, you can write psi as e power plus or minus ikx with some constant k, right? Or you can write it as a cos kx plus b sin kx. Both are equivalent. They both are the same. These are equivalent. Okay.
Wouldn't it also have c cos kx plus d sin kx also?
C cos kx. C cos what?
So like psi has one positive, the e raised to plus ikx and e raised to minus ikx.
Yeah.
So it will have two parts of it.
Yeah. Okay. So basically, if you put a k minus k for this k, the cos function is even function. So cos kx is equals cos minus kx, right? So that is not going to change much.
Yes.
And here, the sin kx becomes minus sin kx if you replace k with minus k, right? And that minus can be absorbed into this constant. So the sin kx remains sin kx, and you get a negative sign outside, which can be absorbed in b. Do you understand?
Okay.
So, okay. So both are essentially the same thing. Okay.
Yes.
Okay. So now our goal. Now we have found the solution. Psi of x. We know the solution. Psi of x is a cos kx plus b sin kx. Now we have to apply the boundary conditions. Okay, to find a and b, we have to apply the boundary conditions. Okay, so what are the boundary conditions? The boundary conditions are x equals psi of x equals 0 is 0, psi of x equals a is 0. Right? At the boundaries, here and here, the wave function must go to 0. Right? Otherwise, you lose continuity.
Yes.
If the wave function doesn't go to 0, we know that here the wave function is 0. X less than 0, the wave function is 0. If it doesn't go to infinity, it is here. So there is a discontinuity. You cannot have discontinuities in your wave function. Am I right?
Yes, sir.
So psi must go to 0 at the edges. Okay, so if you apply that, then your psi of x is a cos kx plus b sine kx. Psi of 0 is a, right? Is
Yes,
0.
sir.
This must be 0. A must be 0. So this term is gone. Okay, so psi of a is some b sine ka is 0. All right, so what does this give you? Okay, we can ignore the b.
A
We cannot.
equals
Okay, b cannot be 0, so we can ignore the b.
E
Sine k, yeah, k equals 2 pi over 2 pi n over a. Am I right?
Sir, only n pi. N pi by a, sir, only. By 2.
Sorry. Okay. Okay. Thank you. Okay. Pi n over a. All right.
yes, sir. Yes, sir.
Okay. So basically,
sir.
this is where you get your quantization condition. You see the n is integer. You know that the n is integer. This is where the discreteness of quantum levels come from. When you say S, P, D, F, and all that, those are discrete energy levels. Is it not? So where do these discrete energy levels come from? It comes from here. This n is an integer. What does this mean, by the way? What does this mean? Okay, so you have a sine kx function. You have a sine kx function, and you have a steep barrier on both sides. And now this function must go to 0 here and here. So what kind of functions do you imagine here? This is your wave function, and the wave function must go to 0 at the edges. Okay, so what kind of sine functions can you imagine which goes to 0 at these 2 points?
the sine graph between 0 to pi,
Yeah.
0 to pi, 0 to
Yeah.
3 pi, like that.
Yeah, so this is one function, and this is another function, and this is another function, right? So you have
Yes, sir.
discrete set of sine functions that satisfy the boundary condition. Not all sine functions satisfy the boundary condition. Only a discrete set of sine functions satisfy the boundary condition, right?
Yes, sir.
So only those discrete functions satisfy that satisfy the boundary condition are possible solutions. No other solutions are possible. And for each one of
Sir.
these, yeah.
Sir, is that n related to the principal quantum numbers that we study?
This is the same as principal quantum numbers.
That n, that n pi by k, that number is the n is the principal quantum number.
When you say principal and all those other quantum numbers, those related to atoms. Okay, where atoms are 3-dimensional, so you can have many other quantization conditions. Here we are quantizing energy. Okay, so if you go for higher 3-dimensional ones, you can quantize angular momentum, you can quantize spin. Okay, so for each one of that you will have a quantum number. Here we are only quantizing energy, so you have only n. There the quantization of energy gives you n, quantization of angular momentum gives you L, quantization of spin gives you m, and all that. Okay,
Okay,
here,
sir. Okay, sir.
here it is just one dimension, so we only have energy. There is no angular momentum. You need to have you need to be at least in the 2-dimensional space to have angular momentum, because the particle can go in a circle only in 2 dimensions, right? It cannot go in a circle in a 1-dimensional thing, right? So you cannot have an L or M or here, nothing here. In 2 dimensions and 3 dimensions, you can have M, L, and S. Here too, we have S here. We have the spin quantum number here, but we are not talking about it. We're ignoring that. Okay, this n is in essence, this n is very similar to the principal quantum number. Okay, in 1 dimension, it is the principal quantum number. Okay.
Yes.
Yeah.
Got it.
Okay. So you have discrete wave functions, and the discreteness. Where does the discreteness come from, by the way? Then
The sine function.
if you take if you make this distance 0 to a, if you make this a, if you take this a to infinity, will you have this discrete spacing between different wave functions?
No, they will be overlapping kind of.
So the point is the boundary. It is the boundary condition that makes this discreteness, right? Because you're restricting the particle within a finite space. This it's the boundary condition that makes discreteness, right? If you're not making it discrete, okay, if the length is long, you can have this wave function and another this wave function. They are nearly of the same energy, very closely, if this length is really, really long, right? So you can have many energy levels within a really short region of energy, many energy levels if the length A is wrong. Okay, if the length A is small, then your energy levels are well separated. This is A large A. This is for small a. Okay, in the limit of A tends to infinity, all this will become a single line. All of this becomes a single line. Okay, there is no energy splitting.
So I have one question. So on the previous page, we have defined something. Can you please go ahead that? So here k is equal to pi n by a. So I'm assuming a specifies a position in the space.
You're assuming what?
So that a is a dimension of a position, like a specify a coordinate of some position in the space.
Yeah, this is the dimension of L. Yes.
Okay, sir. So then if we take like a is equal to pi n by k, then we are getting an exact value of length, like exact value of position. So isn't that the contradiction of quantum theory that like we can't predict the exact position of the space and velocity and position in a quantum theory? So but here we are giving the exact value of pi n by k that gives us a specific value of x.
Okay. So there is some confusion there. Let me clarify that. This a here is not a position. It is a parameter. Okay, the particle is not located at A, right? The particle, you cannot find the particle at A. Psi of A is 0. Okay, so the position is given by everything that you measure about the particle is in psi, is in this function. Okay, the A here is nothing but a parameter. It just tells you the width of the potential well. Okay, so it's a parameter. It's precisely defined because the width is precisely defined.
Okay, sir.
Okay. So A is not exactly a measurable quantity. I mean, it's not a dynamic quantity. It is a given quantity. Okay, it's a parameter. Okay. Okay, when you design there are really physical systems that you can design to make this particle in a well reality. I mean, you really can have a particle in a potential well. Physical systems like if you have gallium arsenide and aluminum gallium arsenide crystals. So these are gallium arsenide crystals, aluminum gallium arsenide, and this is gallium arsenide, and this is aluminum gallium arsenide. Okay, so you can create these kind of super layers, super lattices, and you can confine the electron within this region, within this really small region. Okay, this basically is an infinite potential well. You can create these infinite potential wells in the lab, actually. Okay, so people have done this. People have done these kind of super lattice infinite potential well things, and they have so there the width of the gallium arsenide well can be precisely defined. How many atoms thick it should be. You can have 10 atoms in the gallium arsenide thickness. You can have 20 atoms. You can precisely define that. So you can precisely define the A. Okay, so A is not a dynamic parameter, dynamic variable. The A is a constant defined by the experimentalists. Okay, does that make sense? Okay, so well, let's continue. So you have multiple wave functions, and the energy difference between these wave functions comes about because of the boundary conditions, because of the finite length of the potential well, that is A. If A tends to infinity, then your discreteness is gone. Only when A is finite, you will have discrete energy levels, because you can only fit in curves with 1 node, 2 node, and 3 nodes and all that, or 0 node and all that. Does that make sense? Are you guys with me?
Yes.
Okay, this is an extremely important point. This is where the quantization comes from. In quantum mechanics, the whole quantum idea, the quantum in the quantum mechanics, okay, that's basically discreteness. Okay, and that discreteness comes about primarily because of the boundary condition. Okay, all right. So I don't want to elaborate any further. We don't have time. So you psi of x equals some constant b sine n pi over a into x. Okay, but we know that k square is 2me over h bar square. Okay, this is just a parameter that we introduced, right? So now k square is n square pi square over a square, right? From this you can get e. Okay, so n square pi square h bar square over 2m a square. Okay, so this is an important equation. You have the value of energy of the particle, and the energy of the particle is proportional to n square, and it is inversely proportional to a square. Okay, and E is discrete. For n equals 1, you have certain energy, n equals 2, you have certain energy, and all that. E is discrete. This is discrete. All right?
Yes, sir.
Okay. Now you have basically, this equation gives you everything that you need to know, but we don't know B. How do you determine B? What is the physical approach that you need to use to determine B? What is it? Any ideas? You have to figure out what is psi. What is psi? Psi is?
Sir, we have to find the probability amplitude. Then we will compare the sine curve with that the value of x, and then we will manipulate the sine curve with the amplitude, probability amplitude, and we will get B.
You have to have another constant to get the value of B. You have to have some kind of a constraint equation, a constant equation. Okay, the equation comes from here. So this is probability amplitude, and what is psi x square? What is this point? 0 to a is 1. Okay, so
Yes,
this is a constraint that you have to use to find B. Okay, so this is called a normalization condition. Okay, so all wave functions, any wave function that you're going to derive from any for any potential, it has to satisfy this condition. Okay, all right, it has to satisfy this condition. All right, so now if you do this, you're going to evaluate B is square root of 2 over a. Okay, I'm not going to do that, but B is square root of 2 over a. So your wave function basically is psi of x equals square root of 2 over a sine n pi over a x. This is your entire wave function, and your full wave function is basically this is nth level. Okay, 2 over a sine n pi over a x times e power minus I. Now we know what E is, right? N square pi square s square over 2ma square t. Okay, this is your entire wave function, right? For the nth level. Am I right?
Yes,
Are
sir.
you guys with me still?
Yes, sir.
So I just multiplied psi of x and phi of t. We started off by dividing them. We found the solutions individually for each of them, and we multiply them back together to get the full wave function. Simple, right? So far, okay?
Yes, sir.
Okay.
Yes.
All right. Now let's go to the most important part of this derivation, an extremely important part. You guys have to completely follow me. Okay. Now, this is a linear equation. Schrodinger equation is a linear equation, right? So linear equations satisfy what principle?
Superposition principle.
Good, superposition principle. So you have a psi, that's a solution, some solution equals psi of 1, psi of 2, psi of 3 plus all that. Any solution psi 1, okay, I just wrote down psi n. N can be 1, 2, 3, 4, whatever. It is an integer though, right? So this psi can be a superposition, let's say C1 plus C2 plus C3 plus C4, I4 and all that. And this will also be a solution, right? This composite psi will also be a solution, right? Am I right
So
or
what
wrong?
is
I'm sorry?
so what is C1, C2, C3?
Oh, constants. Those are just constants. It's a linear superposition. So if you have
Like, is it the certain psi 1 type of waves superimposing and certain number of psi 2 waves superimposing like that?
I will tell you this the physical interpretation soon. Okay, it's coming. Okay, it's coming. Okay, I'll let you know what it is. Okay, I will let you know what it is. Hold on for a minute. Okay, let me first go through the mathematics part a little bit, and then we will go for the physical interpretation part. Okay, but this is non-controversial, right? It's okay, right? You guys understand this. For this is Schrodinger equation is a linear equation, and linear equations obey superposition principle. So for any solution psi 1, psi 2, psi 3, you can add them together, multiply by some constants, and create another solution which also satisfies Schrodinger's equation, right? So now any general Schrodinger's equation, any general, a very general Schrodinger's equation can be written like this: Cn for some n equals 1 to infinities. For some n, okay, you have 2 over a sine n pi over ax e power I ent over h bar. You know what en is, okay? En is n squared pi square h bar square over 2m square. Right? So this is it's a new wave function. It's a composite wave function, which is a sum of a lot of eigenfunctions. These individual wave functions, psi 1, psi 2, psi 3, are called eigenfunctions. And for each one of them, you have E1, E2, E3. Those are called eigenvalues. Okay. You guys might have heard of eigenvalues and eigenfunctions or eigenvectors in diagonalization, in matrix diagonalization. It is the same thing here. It is exactly the same thing. These are eigenvalues and these are eigenfunctions. The psi 1, psi 2, psi 3 are eigenfunctions. Psi 1 corresponds to the energy level E1, psi 2 corresponds to the energy level E2, this corresponds to E3 and all that. Okay, psi 1 is an eigenfunction and E1 is the eigenvalue. Okay, and any general wave function can be written as a linear superposition of a number of the eigenfunctions multiplied by some constant Cn. Okay, now let me ask you, is this solution, this psi n, is this separable? Can you separate this as some psi of x comma phi of t? Can you do that? Is it separable? Can anybody? Is it can this function, this psi of x comma t, can this be written as this?
So
Anybody?
like for general cases, it not be the case, but
Yeah.
that's
Yeah.
you have assumed constant in the earlier cases that in that specific cases we can take.
Yes. So for eigenfunctions, if you have eigenfunctions, you can do this. But if in a general case where you have a linear superposition of the eigenfunctions, you cannot do this. It's impossible. So what happened was we constructed a solution which is not separable from separable solutions. Okay. By the way, this is the standard approach. Okay, so you write down, you solve the Schrödinger's equation, you write down the Schrödinger's equation, and then you add those solutions up to make the general psi. This applies for every quantum mechanics problem, not just this particle in a potential well. Every single quantum mechanics problem goes the exact same way. All that you have to do is write the Schrödinger's equation, do a separation of variables, solve them independently, time dependent, you get a time independent h psi equals e psi equation, and then you have a time dependent, you have the time part, which is e power minus I omega t, et over, e power minus I omega t, or I et over h cross. So that part is separate, and you solve for the time independent part, multiply them together, add all those solutions, and you get the general solution. This is the, so let me write that down. Okay. Separate x and t variables, x and t parts. Basically, write psi of x, phi of t, psi equals, and then solve for psi and phi separately. Okay, and third.
So I have a question.
Mm-hmm.
So what we have derived till now is for the infinite potential build that extend from 0 to A,
Yes.
if I'm right. So assuming that there are two infinite potential well extending from 0 to A, and there is some gap, and then it will from B to C. So all the equations that we have derived till now, will that hold at that system also? Because till now we have worked on only one thing and assumed that after A everything is there is no there is a high infinite potential, so probability is 0. But now we are assuming that like there is some place between A and B where is 0, but after B there is place between B and C where the particle can be found. So assuming that there are two cases, like n cases.
Yeah.
Will
I will
that
come
be
to. Yeah, I will come to that question. I will come to that question. It's a good question. It's a good question. Let me come back to that. Okay, I'll come back to that. Okay, just give me a second. I'll come back to you. Okay, so you have to solve for psi and phi separately, and then you write the general solution as phi n times psi n. Okay, and then fourth, you create a linear combination of eigenfunctions psi n, which is basically psi equals summation cn psi n. Okay. Yeah.
Sir, in this, the first steps you had written, like at the end, we are getting a general solution for any wave function we can represent, which
Yes.
is the summation of all possible cases. But sir, how does this like summation of all possible cases make up a general equation? Like for example, we have a differential equation of the second order. Like we just write d like when we write the second order differential equation equal to some constant k. So when we integrate it like once or twice, depending on a specific condition, we will arrive to a function. Right. So like the differential equation in second order represents the all possible equations which might follow a general rule.
Yes.
They weren't just the sum of all this, right? So how are we representing a general thing as a sum of all?
So let's apply. Okay. So it basically it boils down to the superposition principle. Okay. If there are okay, I don't know how to physically explain that. Well, okay, each of these solutions satisfy your Hamilton's equation, your equation, your h psi equals e psi, right? Each of the psi n satisfies this, right? Am I right?
Yes.
Okay, each of that satisfies that. Okay, now let's go ahead and apply that for the complete solution. Psi is Cn psi n, right? This is the complete solution. This is a full solution. This is not an eigenfunction. These are eigenfunctions. Okay. Now let's use this psi on h psi equals e psi kind of thing. So let's figure out what this e is. Okay. Now if you apply that, then h summation Cn psi n is summation Cn En psi n. Right?
Yes, sir.
Okay. Okay, I haven't introduced something else here. I haven't introduced orthogonality. I need orthogonality here. Okay, we are going down a rabbit hole. Anyway, so what I can do is I can multiply this by another psi m h summation Cn psi n. Okay, you can integrate this over x. Then what you would get is basically Cn En delta Mn. Now delta is the delta function. When m equals n, then this is non-zero. When m equals n, the delta Mn is 1. M is not equal to n, delta Mn is 0. So this eventually would give you Cn En. Sorry, not summation. There is no summation there. Okay, I don't want to confuse you guys. Let me step back. So the answer to your question is superposition principle, but it'll come out later. Okay, I have to say something about the orthogonality before that. So
Sir, otherwise you continue with the normal, like at the later on it might get there.
Okay, let me step back. Okay, so what we have done is we have taken this equation and we have solved for psi, right? We've solved for psi. Psi of x equals some square root of 2 over a sine n pi over a x. Okay, psi n of x. Right? We have multiple such solutions. Am I right?
Yes, sir.
For n equals 1, n equals 2, n equals 3, and all that. Now let's do this. Psi m of x dx over 0 to a. Okay, this psi and psi m, they vary only over 0 to a. The particle is not found below 0 or above a. Okay, so our limits are 0 to a. What is this thing? Can you guys imagine this integral? Can you guys do this integral in your head?
It will become like it will become something root of 2a integration of sine something new, like integration of a new sine function ultimately.
But think of it in terms of graphs. Don't think in terms of functions. Think of it in terms of graphs. Okay, let's say this graph is like this. Let's say this graph is like that. What is the integral?
Some of those.
What is the integral
Some
of this?
of those.
Not some of those. You're multiplying these two. You're multiplying this with this. And then
It will like become root of,
Say 0.
like it will
It's
become
zero. Good. 0. Okay, there is exactly half on the positive side and half on the negative side. Right?
Okay.
You understand that? So you have this function, and let's say you're multiplying this with this function. What is this?
Again, it will be 0.
Yeah. Yeah, it'll be 0 unless you have the same wave function. Unless you have the same wave function here and here. If this is the case, then it is not 0. Okay. If this is the case, it is not 0. If this is the case, this function becomes psi n squared dx, which is 1. If they are the same function, this is 1. If they are different functions, then this is 0. So what mathematical quantity describes that? Delta mn. Right? You guys have you guys know about this function, right? Delta mn, Kronecker delta. Have you guys come across this thing, this function, Kronecker delta?
No, sir.
So no, sir.
No. Oh, okay. So you will face this function all the time in quantum mechanics. Delta mn is equal to 1 if m equals n. Delta mn is 0 if m not equal to n. It's a simple function. It's called a Kronecker delta. Kronecker delta function. Okay. All right. So you have two functions. When you multiply two functions that are different, you get a 0. Multiply them and integrate over. When you multiply the same function, you get a 1. Does it remind you of anything? You multiply same thing, you get a 1. You multiply different things, you get a 0. What is that? Does it remind you guys of anything?
Dot product?
Yes, good. I dot j is 0. I dot I is 1. I dot k is 0. Dot product, exactly. Exactly. Doesn't it sound like a dot product?
Yes.
Okay,
Yes,
good.
sir.
Good. We are making progress. Good. So basically, these I and j are orthogonal to each other, right? I and k are orthogonal to each other, right? So if you think of if you think of this thing psi n of x, psi m of x dx as some kind of a dot product between psi n and psi m. Okay, when I say a dot product, I'm writing the dot product like this. Okay, I'm not saying psi n dot psi m, but I'm doing this. Okay, this is basically a dot product. Okay, this is delta nm. Right? So this means psi n and psi m are orthogonal. Just like I and j are orthogonal. Am I right? Are you guys still with me?
Yes, sir.
Okay, so all the wave functions are orthogonal to each other. Any psi 1 is orthogonal to psi 2, psi 3, psi 4, all of them. Psi 2 is orthogonal to psi 1, psi 3, psi 4, and all of them. Every wave function is orthogonal to each other. So what do you have? So you have a vector, this is psi 1, and you have another vector, this is psi 2. You have another vector which is orthogonal to both, which is psi 3. You have another vector which is orthogonal to all the other ones, which is psi 4. They are all orthogonal to each other. Can we imagine like that?
Yes, sir.
Anybody else? That yes was kind of sleepy. So you have
more than 3 vectors can be orthogonal to each other.
yeah, but these are infinite dimensional vectors. These are not just, these are functions. They can be orthogonal to each other. Your vectors, these psi n's are not 3-dimensional. You can think of them as infinite dimensional vectors.
Okay.
Okay, so in infinite dimensions, you can have infinite vectors that are orthogonal to each other, right? So basically, physicists
Yes, sir.
in quantum mechanics always work in infinite dimensional spaces. And that infinite dimensional space is called a Hilbert space. Okay, Hilbert space is occupied by functions. It's unit vectors like I, J, K for unit vectors for 3-dimensional spaces. The unit vectors for Hilbert space are psi m, psi n, and all that. These are the sine functions, sine n pi over a x. These sine functions form the unit vectors for the Hilbert space. Okay, so basically every vector here, this vector is sine 2 pi over ax. This vector is sine pi over ax. This vector is sine 4 pi over ax. Okay, each vector has its own sine function, and they are all orthogonal to each other. Okay, if you define orthogonality like this integration. So you have a you have an infinite dimensional vector space where each function is a vector. Think of each function as a vector. Right? Do you guys with me? Are you guys still with me?
Yes, sir.
Are you guys confused?
No, sir.
No, sir.
You're good, right? You're good, right? This construct, by the way, this construct is extremely important. This infinite dimensional construct, infinite dimensional vector space is extremely important. This will come over and over and over again in physics. Okay, in mathematics also. If you go to Fourier transforms is exactly this. I will come back to that if time permits. Fourier transforms is basically an infinite dimensional vector space. Fourier transforms is a rotation in an infinite dimensional vector space. That's it. Now it's not a rotation, it's a decomposition. Okay, so this construct is extremely important in physics and mathematics. Okay, so that's why you have names like this, Hilbert space. When you say Hilbert space, all physicists know. What do you mean? You mean what do you mean by Hilbert space? You mean an infinite dimensional vector space where each vector, each unit vector is a function, is some function. It can be sine function, it can be a Bessel's function, it can be a Legendre function. There are many functions like this. They are called orthogonal polynomials. Okay, there are many orthogonal functions like this. Okay, so if you want to start doing quantum mechanics, you need to be comfortable dealing with infinite dimensional vector spaces. Okay, so I'm not threatening. It actually boils down to be pretty easy. Okay, quantum mechanics is really easy mathematically compared to other physics areas like statistical mechanics, like thermodynamics. They are extremely difficult, but quantum mechanics is really easy to do. Okay, because it's a linear theory. Right, now you have an infinite dimensional vector space with each vector is a sine function, sine n pi x over a, sine pi n pi a over x. Okay, each vector is a sine function. Now, what if I have to denote a general vector? These are all unit vectors. Okay, it's like I, J, K, L, M, N, O, P, whatever. Okay, these are the unit vectors. Okay, now if I want to find a general R vector, what would I do? I take some amount of I, okay, some E1I, C1I plus C2J plus C3K plus C4L, and so on, right? This is my general vector, right?
Yeah, yes, sir.
Am I right? So basically my I is a sine function. So what I do is instead C1 sine 1 or pi over a times x, C2 sine 2 pi over a times x, and so on, right? So this is my new R, right? This is my new position vector,
Yes.
right? So just like that, I'm going to write my psi as summation of Cn psi n equals 1 to infinity. This is basically linear superposition. Am I right? So basically, these are my ijk's. Okay, and these are the coefficients that basically tell you how much I is in psi. Does it make sense? Are you guys with me still?
Yes, sir. Now that summation of in general makes sense.
So yeah, so basically I just wanted to come to this point to answer your question. Okay, is your question answered?
Yes, sir, yes, sir. That vector summation makes sense.
Okay, so basically it's a vector summation. Okay, this is basically a vector summation in an infinite dimensional vector space called Hilbert space. Okay, and the important quantity that you need to remember is psi n psi m dx is delta mn 0 to a. This is called orthogonality condition. Okay, this makes your life easy in quantum mechanics. All these functions are orthogonal. They are all perpendicular to each other. All this psi n and psi m's are perpendicular to each other. Okay, so it makes your life easy actually for calculations. You will see later on. I don't think we are going to do any proper quantum mechanics problem. So let's say you take a wave function for in a hydrogen atom. Let's say you take a wave function for s orbital, and then you take a wave function for p orbital. If you do this psi p, you will get 0. Okay, those two vectors, psi s function for psi s and function for psi p orbitals, they are orthogonal. Okay, you will get a 0 there. Okay, so these are orthogonal functions, and orthogonal functions are extremely important in mathematics and of course physics. I mean, have you guys heard of orthogonal functions in mathematics? In your math lectures?
Yes, so we have heard about the orthogonal trajectories in differential equation and vector and 3D maths.
Okay. You will keep hearing more of this. Okay, you will keep hearing more of that. There are a lot of orthogonal polynomials, and quantum mechanics is full of them. Okay, all right. So basically, this is the machinery of quantum mechanics. This is the machinery of quantum mechanics. So what you do is, sorry, the list. Where did I have the list? Okay, separate the variable, find the wave function, find the eigenfunctions, and then put them together. Okay, and then do the linear combination of all the eigenfunctions to get the general solution. Okay, this is possible because the functions are orthogonal to each other. This kind of construct, this kind of linear superposition is possible because the eigenfunctions are orthogonal to each other. Okay, this procedure is common for all of quantum mechanics. Okay, this is what you do when you solve a quantum mechanics problem. This is what Heisenberg and Schrodinger and everybody did after they solved many problems, many quantum mechanics problems. They started out doing this, exactly this. Okay, it is not that this procedure is invented by Schrodinger and Heisenberg. No, this procedure has been around for 200, 300 years. Okay, because Fourier transform was discovered in 1800s, And this is the exact same procedure for Fourier transform. Okay, in Fourier transform, this psi n are e power I kx. That's it. That's Fourier transform. If the psi n's are e power I kx, then it's Fourier transform. So Fourier transform is in a sense quantum mechanics. Quantum mechanics is in a sense Fourier transforms. Okay, that's why I wanted you guys to learn Fourier transforms very well. Okay. 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 So basically, we have written down the general solution. All right. The general solution psi is Cn psi n, where psi n is square root of 2 over a sine n pi over a x e power I minus I e h cross over, sorry, e t over h cross, where e n is n square pi square h bar square over 2m a square. Okay. So if a particle is in this state psi, capital state psi, okay, what does that mean? It is in a superposition state of various different, this is psi 1, psi 2, psi 3 and all that, but the particle is in some psi. Okay, if you project it here, this is C1. If you project it there, this is C2. If you project this here, this is C3. Okay, so there is a C1 amount of psi 1 in psi. There is C2 amount of psi 2 in psi. There is C3 amount of psi 3 is in psi. Okay, so your energy of this psi, what do you think would be the energy of the psi? Okay, the psi 1 has energy E1, the psi 2 has energy E2, psi 3 has energy E3. So what is the energy of psi?
Summation of the individual.
Summation of Cn square E, En.
E1 plus E2.
Yeah, but you have to multiply that with Cn square. It's not the summation of the individual E1. There is C1 amount of E1 there, C2 amount of E2 there. So these C1 and C2 are complex numbers, by the way, just like psi n's are. Psi n's are complex numbers, so these C1, C2 are also complex numbers. So you have to take a modulus. So Cn square En, this is your psi. This is the average energy of psi. Okay, now let's go back to this question, to physics. Let's say you put a particle in this composite state. This is a composite state. It's neither in psi 1, it's not an eigenstate. It's neither in psi 1, not in psi 2, not in psi 3, but it's in everywhere. It's spread everywhere. Okay, it's spread in all functions. It has some part of every eigenfunction. Okay, now let's say you measure the energy of this particle. Let's say you measure the energy of this particle. What do you get? What would you experimentally you try to measure the particle's energy? You know that the particle, you prepared the particle in this particular state, in this particular vector. The vector is not along psi 1, it's not along psi 2, it's not along psi 3, it's a composite of all those directions. And you try to measure the energy of that particle. What do you get?
We will not get the complete energy, maybe because we were only able to measure in that particular dimension only, not the higher dimension one.
Okay, you're getting closer. Can you answer? So what is the answer? What would you get? What energy would you get? Would you get this energy?
May or may not.
That's not the answer. The answer is you will not get this energy. This is an expectation value. This is H. This is the expectation value of this energy. You will not get that expectation value. You will get individual values. You will get with the probability C1 square, you will see E1. You will get the value E1. With the probability C2 square, you will get E2. So one time, if you do in an ensemble, if you create thousands of such experiments, and in some experiments, if C1 if C1 squared is 2, 1 over 2, you will get half the time you will get E1. If C2 squared is 1 over 3, you will get 1/3 of the time you will see E2. 1/4 of the time you will get E3, and so on. You will not get this energy. So you have to create this system infinite number of times, which means you have to create an ensemble, okay? And in each ensemble, you have to measure the energy, okay? And if you measure the energy infinite number of times, sometimes you will see E1, sometimes you will see E2, sometimes you will see E3. And if you see the probabilities of how many times you got E1 and E2 and E3, it'll be C1 squared, C2 squared, and C3 squared, and all that. You will only get the definite energies, E1, E2, E3. Those are the eigenenergies. Those are the eigenvalues, energy eigenvalues. You will always get the eigenvalues. You will not get a composite value. You will not get E1 plus E2. You will not get that. Okay. The average energy, then after you got all the values, after you got half of E1 and 1/3 times E3 or E2, 1/3 of the time, if you've created 100 experiments, 33 experiments will give you E2, 50 experiments will give you E1. Okay, then you have to combine them all together and then find the average energy. You have to calculate the average energy. But when you measure, you're not going to get the average energy directly. Do you understand what I'm saying?
So like suppose you're given this psi, we don't know in like what dimension, like in how many dimensions it does have a component E1, E2, E3 whatsoever. But if we measure it, suppose 100 times, like as you said, we get certain E1 times, we get certain E2 times, we get certain E3 times.
Exactly.
And whatever the summation we get after taking the average will always be less than this particular summation n equal to 1 to infinity Cn square En.
Very good. Exactly. Exactly. That is exactly how you do it. Okay.
So, but what if like it was in like the psi what we had was, suppose, had energy projected only in this 3D plane, and we exactly got this like we got it measured in E1, E2, E3, and whatever summation it will get, it can be equal to then En, like very close to at least.
If you're
Like it will not have any energy component in any higher dimension. Suppose it will have only component present in X, Y, Z plane only.
Okay, these psi1, psi2, psi2 are in no way related to real space. You understand that, right?
Yes, sir.
Okay, these are functions. This psi1 is just a sine some kx. These are functions. There's no way. We are still in one-dimensional space. It's k1, k2, sine k3, x. These are all just x. This is one-dimensional space. We are still in one-dimensional space. In real space, we are still in one dimensions, but it's a mathematical construct. What we are doing is it's a mathematical construct. Basically, each vector, we are assuming each wave function as a vector. Okay, this is a vector. This is a vector. Okay, if you go to higher level orbitals, like this is a vector, like this is a vector. Each function, each one of these functions is a vector. We are thinking of them as vectors. The functions as vectors. So this is a vector. This is a vector. This is a function. Okay, this is a function. This is a function. Each one of them are orthogonal to each other just because this sine nx, sine mx is delta mn. That's why. Okay, so this vector space construct has nothing to do with space. Okay, this is a mathematical construct where your unit vectors are functions. I think I have made that clear, right? Okay.
Yes, sir.
These vectors are not. Of course, I use the analogy of ijk, but that's just an analogy. It's not. So this has nothing to do with space. These vectors have nothing to do with space. These are mathematical constructs. It's like numbers. Number is a mathematical construct. It doesn't have a reality. Okay. 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 Boy, was it long. I thought I would finish another problem, another thing, free particle. Maybe not. I will have to finish something else about the velocity of the particle. Can we go ahead a little bit more or no?
No, sir, because today is our exam also, sir.
Okay. Okay. Basically, I've taught the same thing that I've taught before. It's nothing new. Anyway, I want at least two more classes.
Okay.
I'm sorry?
If you ask from other student also, sir, if they are interested, then continue.
Yeah, please. Can you guys please do it right now so we can hang on a little bit more, or anybody? Are you guys willing to hang on, or you want to go?
We need to charge our mobile because
Yes,
we have
sir.
exam.
My laptop battery already is dead.
Okay. Okay then. Okay. All right. So let me stop the recording.